Okay, welcome back to our afternoon session. Please take your seats, get yourselves comfortable. It's my pleasure to introduce our next speaker, Professor Nader Engheta, the H. Natwell Ramsey Professor of Electrical and Systems Engineering, Professor of Material Science and Engineering, Bioengineering, and Physics and Astronomy at the University of Pennsylvania in Philadelphia. Professor Engheta earned his BS degree from University of Tehran, master's and PhD degree from Caltech. And his research encompasses a diverse array of fields, including optics, nanophotonics, metamaterials, nano-optics, electrodynamics, microwaves, graphene photonics, imaging and sensing inspired by animal vision, and in general, the physics and engineering of fields and waves in diverse material systems. Nader has been honored with numerous awards for his contributions to science and engineering, including the 2023 Benjamin Franklin Medal in Electrical Engineering, election to the American Academy of Arts and Sciences, and Academia Europaea, and the Caltech Distinguished Alumni Award. He also received the 2020 Isaac Newton Medal and prize from the Institute of Physics in the United Kingdom, the 2020 Max Born Award from Optica, the 2018 IEEE Pioneer Award in Nanotechnology, and the 2015 SPIE Gold Medal, and the 2014 Balthasar van der Pol Gold Medal from the International Union of Radio Science. Additional accolades include the William Stryfer Scientific Achievement Award from the IEEE Photonic Society, designation as an International Fellow of the Canadian Academy of Engineering, and being named a Fellow of the U.S. National Academy of Inventors. Professor Engheta was also recognized as one of the Scientific American Magazine's 50 leaders in science and technology, and is the recipient of the Guggenheim Fellowship. He is a fellow of many societies, including IEEE, Optica, APS, MRS, SPIE, URSI, AAAS, IOP, and NAI, and has been awarded honorary doctoral degrees from Aalto University in Finland, the University of Stuttgart in Germany, and Ukraine's National Technical University Kharkov Polytechnic Institute. Please join me in welcoming Professor Nader Engheta to the stage to give his presentation entitled Doing Math at the Speed of Light with Photonic Metastructures. Nader, please.
Thank you. Thank you very much, Koray, for your kind and generous introduction. It's a pleasure and honor for me to be here. I'd like to thank my friend, Professor Chad Merkin, and his team for their great efforts in putting this wonderful symposium together and for giving me a chance to be part of the event today. It's truly an honor and pleasure for me to be here. As you can see from the title of my talk, I'd like to discuss how we can use material structures, particularly at the nanoscale, that when they interact with light, they can do mathematical operation at the speed of light. In my group, we are interested to see how we can use metamaterial and metasurfaces in order to structure light and to have useful and novel functionalities. And one of the areas that we are interested to see whether we can actually have material to act as computer with light. So can we have actually a computing machine that works with light at the nanoscale? Now, it's interesting, if you look at the history of science and technology, often we notice that let me make sure this works, okay? Often we notice that the technological development happens when you would be able to actually structure and manipulate certain physical entities. For example, if we can structure, manipulate electrons and photons, we can do interesting things. Of course, this is obvious for all of you in the audience. For those of you interested in electrical engineering, if I show you this picture, which is a circuit diagram of an old-fashioned black and white TV, Obviously, this may bring nightmare to a designer, but if we look at this, effectively what these wires do is to actually design where the electrons go through interesting nodes, and that will define functionality as a TV. Can we do that with light at the nanoscale? So let me show you these two pictures that later on in my talk, I'm going to discuss it in more detail. Indeed, you notice that these pictures, which is about 35 micron and 24 micron in the dimension, how the light actually goes through these structures, basically kind of like a labyrinth of wave. And this structure, by the way, would do vector matrix multiplications at the speed of light. We're going to see that later on, how it is done. So one of the specific areas that in my group we are interested is, can we actually make photonic processing with light at the nanoscale, as I mentioned. In order to tell you how we got interested in this, let me take you back to about 20 years ago. 20 years ago, we were interested in the following questions. By the way, I'm both electrical engineer and physicist, so I'm interested in the question that goes between these two fields. Now, we all know, by the way, in electrical engineering, that we have lumped circuit elements that we teach that to our undergraduates the first course, resistor, capacitors, inductor, and so on and so forth. But the interesting question we were posing at that time is that, could we have nanoparticles that behave as lumped circuit elements, but for light? In other words, could we modularize photonics? Now, why I was interested in that is because if we could come up with those nanoparticles, then we can actually bring the two fields of electronics and photonics together, because they would have a common alphabet. After all, these two fields follows Maxwell's equation, and yet, historically, they evolved separately. Indeed, in year 2005, almost 20 years ago, we came up with a solution. We showed that if you have nanoparticles with a specific shape and materials, and when you send light into them, they would behave as effectively optical lumped capacitor, optical lumped inductor, and optical lumped resistor. And that actually provided us with an interesting path that we developed various different interesting possibilities as to how some of the ideas from electronics will come into photonics and vice versa. Now, one of the specific ideas that we had in the back of our mind is that in electronics, you can put this lumped circuit together, just like an alphabet of a language, and you can make, many different functional circuits, including electronic processor. That's what you have in your cell phone that would work. But can we do that in photonics? So we said, now that we know that we have these elements, which we call it optical metatronic elements, what would happen if we would put them together and we can have a photonic processor at the nanoscale? So with that idea in mind, we said, OK, about 10 years ago, we came out with a series of recipes that we showed that how you can actually define materials that when you send a wave into them, they would actually do mathematical operation at the speed of light. For example, we came up with the recipe as to how you design a material that when you send a wave into it, it could actually do differentiation. It could do integration. It could do the calculus operators that we're all familiar with. Now, one of the low-hanging fruit applications we had in mind at that time is that, could we actually design a material that when this wave goes through this, it could actually do second-order differentiation? And why we were interested in that particular operator? Because you all know that in image processing and image analysis, if you have an operator known as Laplacian operator, which is second-order differentiation, you can do edge detection. So this actually showed us that when we have a structure like this, and when you send a wave into it of an image, in one shot, you can actually get the edge of the image. You don't need raster scanning. You don't need this structure that the digital computation need to have. And this would be extremely fast. After this theoretical paper came out, in 2014, there was a lot of interest in the scientific community in optics and in metamaterial. And several experimental groups followed our approach and indeed experimentally showed that it's possible to have a surface, a metasurface, that can actually do edge detection. We were very excited by this development. We said, OK, now let's put our goal, the more ambitious goal. Now we said that we know how to design a material that would do mathematical operation with light. Can we design materials that can solve equations? So can we actually solve mathematical equations with light? So in order to do that, we decided to start with the most general linear integral equation known as Fredholm integral equation of the second kind. That's a very common integral equation in many different of science and engineering. So we said, OK, now how are we going to do this? We should start with this structure that you see there in the bottom of the picture. That's the way we designed the structure that would do that integral operators. But that's not enough. We also have to have a feedback system. So as the wave goes through this structure, it repeats going back through that. And indeed, it would do what in mathematics we call it the Neumann series. And that's how actually you solve integral equations. So we said, rather than doing that with a regular computer, let the light do the job for us. And that's the fastest speed in the universe, that we can actually get that Neumann series. So we studied this extensively, theoretically, a lot of computer simulation, and then we decided to actually experimentally show this. And for that, we first started to have a scaled-up version of this idea. So we decided to first do the experiment in microwave. And that's what we did. So this is the structure, the first structure we built, and I'm going to show you the photograph in a few seconds, that indeed consists of three materials that you see over here. The orange region that you see in the middle is a microwave plastic material. The yellow region is just air. So imagine this, that you have a piece of plastic, and you create holes in them in a specific shape, and the size and the location. And this, indeed, would solve an equation for you. This shape, by the way, what does this shape remind us? It looks like a Swiss cheese. That's what in my group we call these Swiss cheese metamaterials. And the red region that you see around is just an absorber. So we designed this. This is a rendition of this structure. This is the photograph of what we built in my lab about 5 years ago. And in the bottom, you see the comparison of experimental result with theoretical result. And indeed, it agreed quite well. And this indeed showed that this gadget is, in fact, a computing machine that works with wave. Now, Franklin Institute made a video about our work, and I showed this interesting simulation that we see over here. You see how light actually goes through this gadget, and that's what they call it, the labyrinth of light. So it's kind of like a pinball machine that the photons go back and forth, but what comes out is the solution to the integral equation you have with an arbitrary input. So this was very exciting for us, but remember, our goal was to actually do this in the nanoscale. This was just a scaled-up version that we had. So then, as a next step, in collaboration with two friends, Albert Polman from Institute of Nanophotonics in Amsterdam, and Andrew Alou, who was my former postdoc and student, and now is a prominent faculty at City University of New York, we joined forces, and indeed, we brought this into the nanoscale. What you see there is that Swiss cheese, of course, a different design, that would be on the silicon on sapphire. And the yardstick that you see over here is 500 nanometer. So we were able to bring this gadget, by the way, can solve integral equations. When our paper came out in April 2023 in Nature Nanotechnology, we made the cover page, and we were very pleased with what the caption that the editor put on the cover: mathematics at the speed of light. So this actually we showed that you can actually solve equation. But solving equation is effectively like inverting a matrix. But what other interesting mathematical operation we can do? How about vector matrix multiplication with metamaterial? Now, why are we interested in vector matrix multiplication? Well, in the past 2 days, Nobel Prize in chemistry and in physics were related to AI and machine learning. And indeed, of course, as you all know, in the deep neural network and the artificial intelligent machine learning, you have to deal with these structures that, in fact, represents like artificial neurons and the connection between them. This process, in fact, is vector matrix multiplication, as you all know. So we said, it would be very interesting to see whether the materials can actually do vector matrix multiplication with light. And with that goal in mind, and also the goal that to actually make this in a platform that would be mass producible, we decided to actually bring this idea onto silicon photonic platform technology. In collaboration with a colleague of mine, Firuz Aflatuni, we decided to actually bring this structure as you see over here. What you see over here is the design of a 2x2 and 3x3 matrix that's done on the silicon photonics. I'm going to explain this in a little bit more detail than what you see over here. We send this thing to the foundry. The chip was made, and it was measured, and indeed, it showed that you can do vector matrix multiplication. But let me just pick one example of that, and let me show you a better picture of this. This is what you see over here. So this is another, Swiss cheese platform that would do interesting mathematical operation of vector matrix multiplication. Just to explain to you what you see, this is the top view of the design that we have. Now you notice that this design has a pink region and a white region. What is the pink region? Pink region is basically a layer of silicon on SiO2, 220 nanometer. And the white region is also silicon, but 150 nanometer. Now, why did we do it this way? Remember in the microwave case that I showed you, we had two different materials. One of them was plastic, the other one was air. But if we wanted to do actually two different materials on a case of silicon photonics, the foundries would not do that. So instead, we decided to find a different approach. Rather than using two different materials, we decided to actually use two different thicknesses of silicon, because as the guided wave goes through this, with a different thickness, you have different modal index. As a result, you can actually create that contrast that we want. Indeed, experimental result that we had on this showed that this gadget works, and it would do vector matrix multiplication with the speed of light as the wave goes from left to right. Just to show you the chip we have, if this is the picture of the chip, and you see, actually what you see is this little dot that you see over here, if we enlarge it, and this is the picture you see over here. The scale bar is 10 micron over here. That structure that you see there effectively is about 30 plus micron and 20 plus micron. That will do vector matrix multiplication. So you might say, okay, this is interesting. You can solve equation, you can invert matrices, you can do vector matrix multiplication, but the example you have shown us is only 2x2, 3x3, 5x5. Why not much larger structures? Why not, for example, 100 by 100 or 1,000 by 1,000 matrix? That's a fair question, and we decided to address that as well. So this is one design that one of my PhD students, Vahid Nikah, has done. In this case, it's 10 by 10, and we use the inverse design to come out with this structure you see there. Particularly, please note that this structure is intentionally non-periodic. And that's important, because then you have a lot of spatial modes there that would allow us to do a lot of the mathematics inside of this. We haven't built this yet. This is just to show that our inverse design methodology can give us a larger scale. But still, one might say that if I want to go larger and larger, this becomes more involved and complicated. So we decided to do another approach. We decided to say, okay, rather than having a completely general kernel, let's choose some matrices that would be very useful in image analysis. And a class of matrices in image analysis would be useful is known as banded matrix, which effectively would give you the convolution matrices. These matrices have very interesting properties. You see, the size of the matrix could be as large as you want. It could be 10,000 by 10,000. But actually, the number of variables that you have there is limited. It's around the diagonal terms that you see. So we designed that, by the way, again, on silicon photonic platform. And let me show you two simulation examples that you see over here. One is for this structure, and the other one for wavelet transform. Many of you are familiar with wavelet transform. That's very important in image analysis. So here, we indeed design a system that when you send input into it, what comes out will give you the amplitude of the wavelength that you need to have from that structures. Now, this is the structure that we designed over here. Look at this. This is 32 input, 32 output. And one of the interesting points, by the way, I forgot to mention about this design is that we decided to actually use this idea that kind of like a stem cell in biology. We said, rather than having something that's, 1,000 by 1,000 completely designed from scratch, can we actually design only one small portion of it and then repeat it? And that's what we did, by the way, over here. If you notice, you have 32 elements over here, but these 32 elements, actually, they're all one repeated element that you see over here. But the output is not repeated. In other words, if you send this input to this structure, what comes at the output is this distribution that you see over here. So this structure is capable of actually doing wavelength transform on the arbitrary signal that you see is sent in front of it. Now, back in month of June, just about 4 months ago, we actually designed this for silicon photonics. This is a structure that we designed. There's a lot of detail going on that I'd be happy to talk to you offline if you're interested, the way we designed this. And in order to bring the light into it, we got inspiration from the old-fashioned horn antenna that you see on top of it. But we brought that idea on the silicon photonics with a thickness about 220 nanometers over here. And this is the structure that we bring the light into it, and that comes over here. We finished this design, and on June 14, we sent it to Foundry. And we are waiting to receive the chip. When the chip comes, we're going to test it, and we'll see what happens. We are very excited about this, that this structure, using the inverse design, when it comes, can actually do the wavelet transfer. OK. Now, I mentioned about spatial mode and the advantage of that in optics. You might say, OK, so what's the advantage of optics? Why do you want to do this with optics? One of the interesting points about optical system is that as you see from the structure I showed you over here, you see intentionally this inverse design structure is not periodic. And as a result, you have a lot of spatial modes that's going through this. That would allow us a very good number of degrees of freedom that we have there. So that's one of the interesting points about optics, because you can actually have a lot of spatial modes there. But there's another interesting advantage for optics, and that is you can actually do frequency multiplexing. In other words, can you design one single structure that do two different mathematical operations with two different lights? But the structure is the same. Now, we all know, by the way, that the light with different frequency can go through each other without affecting each other. So that's what we decided to do. We went back to the drawing board. This is very similar to what we did before, except this time, when we want to design the Swiss cheese that you see over here, it would do more than one operation. When you operate this system with frequency omega 1, it would do one set of kernel. But the same structure, if you operate it with a different frequency, it will do another operation. And we built this system. And this system, we built it, and the experiment, we did it in microwave. Now, we would like to bring that into optical system. So if you operate it with the 4 gigahertz, it solves one set of integral equation. The same structure, at the same time, if you send another signal with the 5 gigahertz, it will solve you another integral equation. So in other words, one single structure can do more than one operation. And that becomes quite fascinating. Electronics would not be able to do that. Electronic computers cannot be able to do that. But this will be able to do it, because you can actually bring different lights into the same structures. Now, I'm going to pose 3 questions over here. So far, we have shown that we can do vector matrix multiplication with a possible application towards AI and machine learning that would do much, much faster operation. 2, we are able to actually solve equations, meaning inverting the matrix. 3, we can do it more than one in the same structures. But then the question is, can we actually use this technique to solve algebraic equations? Now, what I showed you over here was an integral equation or differential equation. But can we do algebraic equations? So, for example, if you give me this equation, can I solve this equation with light? So the idea would be similar to what I said, except that Swiss cheese that I have to design over here would not be an operation, but it would be a nonlinear system. So one of my students, Engheta, has done a great job in this design. This is work in progress. This is one of the design we have. We haven't built this. This is what design we have. And indeed, this system can actually solve that second order equation with light. So this is the computer simulation that show how actually, as you change the parameter C, this actually will give you the solution to these quadratic equations that we have there. The second question I'd like to pose is that, can these structures solve eigenvalue problems? Now, why we are interested in eigenvalue problems? For quantum physics. Of course, as you all know, quantum physics is full of eigenvalue problems. If we can actually design a structure at the nanoscale that can solve eigenvalue problems with light, that would be quite helpful for us, in attacking many of problems in quantum physics. So here we have a very preliminary results that my student has done. And indeed, it's possible, at least in the very preliminary result, that we will be able to actually see the eigenvalues of this equation using the wave that's going through this. And the third question I would like to pose is that everything I showed you so far, by the way, was a coherent system. In other words, you need to use a light with magnitude and known phase. But can we actually do this with incoherent light? In other words, one of the visions we have is this one. Will it be possible to actually have an optical computing machine that works with LED? If I can do that, the cost will come down significantly to do that. Again, we have some promising and encouraging result. Here, there's one interesting method that we are studying right now. This is work in progress, that we show with the ray optics, we would be able to invert a matrix that we have over here. So we'll see how it goes. This is work in progress, and we're very excited about these possibilities. And finally, Koray, how much time do I have? OK, very good. So up to now, what I've said is that we design nanostructures that when you send the light through it, it can do vector matrix multiplication. It can invert the matrix, meaning it can solve integral equation and differential equation with light. It can do parallel processing. That's very important as well. In other words, the same structure can do more than one operation at the same time. And those three questions I pose as basically some of the work in progress that we are doing there. But everything I've shown you so far is that when we design that Swiss cheese and we build it, it's fixed. Wouldn't it be interesting if we would be able to change that? In other words, to make it reconfigurable, to make it programmable. Because if we can do that, that would be quite interesting. And we are working on that. So let me show you again some preliminary results that we are actually looking at it. I showed you this picture before that was our work 5 years ago. Right now, what we are doing is that rather than making actually this Swiss cheese metamaterial to be inside the material, what we are saying is imagine that you have a silicon waveguides, and you put only a thin layer of phase change material on top of it. And then you do the inverse design to make that phase change material. Now, phase change material, there are materials that you can actually change their properties, let's say thermally. Or you can put some other form of material that would be electro-optically, you can vary in that. In that case, by changing the value of the parameters of the top layer, you can actually change the matrix. And when you change the matrix, you can actually program that. So here is some theoretical results that we are getting right now, which show us that it could be possible. We'll see. Here, we are showing what would happen if we start with the simple material, and then we change the permittivity of the material. And indeed, we show that the matrices will change. But you might say, OK, if we can do that and we can have a reconfigurable material, what good does it do? OK, so let's assume we can do that and we can change that. Would reconfigurability be helpful for us? In order to answer that question, we said, OK, let's do two things at the same time. While we are studying those phase change material to make it reconfigurable, let's see what would happen if we do have a system that's reconfigurable. So we decided to build an electronic version of our ideas. And that's what we built in my lab over here. Now, this was just to show the proof of concept what good reconfigurability would do. What you see over here consists of 5x5 matrix elements that consists of 25 elements that you see over here. We put it in 5 racks over here. Each rack, you see 5 elements. What are those 5 elements? Those 5 elements, basically, we call it multiplier. It consists of an amplifier and attenuator, and it consists of phase shifter. So that means what? That means we can have a 5 by 5 matrix that we can change its element at will. Okay, that's one thing. And second thing that doesn't show in this picture is that the output of this 5 by 5 come out and go back. So there's a feedback system. And remember, I mentioned to you at the beginning of my talk, when we have a structure that there's a feedback system, we would be able to invert the matrix. So this system is capable of solving equation 2. And it does invert the matrix. But here's one additional advantage. It's changeable. So because we can actually change the amplification and we can change the phase shifting of this, you can actually change the matrix. So now think about this. I have a matrix. I can invert it. Based on the result of inverted matrix, I can go and change the matrix and invert it again. Go and change it again and invert it again. So then what good does it do? Optimization. In other words, this system is capable to do optimization on its own. And we decided to actually apply this to 2 problems. So first, let me take a look at some of the early results there. This experimental result comparing what we found experimentally to the matrix we put there. The bottom part shows the result of an inverted matrix. And you notice experimental results agreed with the mathematical result of the matrix inversion. So that was a good thing that we started. And then we say, OK, let's apply it to 2 problems. One problem is a root finding. What do I mean by that? If I give you a 5th-order polynomial, complex numbers, and I ask, can we actually find the root of this 5th-order polynomial? There's a known technique called Newton root finding. What you need to do is you start with a guess at the beginning, then find the Jacobian matrix of this, then invert that matrix and multiply by this, and you get the next one. And this process, as you continue, converges to the root of this. But you notice in this process, we need to invert a matrix. That's where our gadget comes into play. Our gadget is capable of inverting the matrix, and every time we invert it, we can go back and do it again. So we decided to apply this problem to our system, and indeed, it solved the problem. So this gadget actually was able to find the root of our system because of reconfigurability. Imagine that in the future, when we actually do this thing optically on our phase change material, something at the nanoscale would be able to actually find the root of your system. You can solve an equation. You can invert the matrix. You can do vector matrix multiplication. And finally, as the last slide, we said, OK, what we have used so far is we use the inverse design to design that Swiss cheese. And inverse design is an optimization. So we said, wouldn't it be interesting that this gadget that we have actually design another gadget? In other words, can we actually do the inverse design using these inverse design structures? After all, what is the optimization? Is the process I mentioned to you. You start with a point, you find the inverse. Based on that, you go and change the matrix, you do it again. Go and change the matrix, you do it again. Let that thing done by this system and hopefully by light in the future. So we decided to actually apply it to this problem. Imagine that you have 5 scatterers. So imagine you have 5 rods sitting over here. The location of these rods are known. The size of these rods are known. But the materials are unknown. And then we pose this question. What kind of material should I use in these 5 rods such that when I send a wave into it, and of course scatters, at these 4 arbitrary points, I would like to have specific scattered field, magnitude and phase. Can we go and find what those materials should be to give us that? Well, that's the inverse scattering problem. People in radar deal with that, but they have a lot of difficulties because they have to do many simulations to get to that point. So we said, can our gadget actually give us that solution? It did. This gadget indeed gave us what those 5 materials should be in order to get the required and the desired scattered field. That's one of the reasons, by the way, we put this title, a metastructure that can design metastructures. So our goal is to actually show that in the optical system. Here is the electronic version that we showed that indeed is capable of doing that. That brings me to the end of my talk. So let me thank some of the members of my group that contributed significantly to what I presented to you, and also some of the collaborators that we have worked together. I'm very fortunate to have this collaboration and the group, and I'm really thankful and grateful to all of them. So in summary, first, I want to thank Chad and also his team for putting together and giving me a chance to be here. And I hope I was able to actually tell you the excitement that we have about this approach to this. Can nanostructures material, when it's interacting with light, can become actually an optical computing machines? And what we have shown over here that indeed is possible. We are very excited about this. And eventually what I envision is that this type of computing at the nanoscale will be combined also with the electronic one. And that would be quite fascinating to have a hybrid system. Because there are things that optics will do better than electronics. And I'd be happy to talk to you about that if you're interested in those things. But there are things that electronics can do better than optics. So the best is a hybrid system that we have. With that, I'd like to thank you so much, and I'd be happy to answer any question you have. Thank you.
Well, thanks. Thanks, Nader, for the inspiring, great talk. So now the floor is open for questions. So on the left, can you please stand up that Nader can see you?
Hi. So I had a question about if you could potentially make a generalized computing device using these photonic materials, like that would be essentially Turing complete. And if so, what would be like the basic components required to do that?
Thank you. So let me repeat the question. You're talking about generalized computing. Are you talking about all-purpose computing?
Yes, exactly. Yeah.
No, I would not say that. The important thing, by the way, is to realize what optics can do. One thing, by the way, if you're interested in digital computing, electronics is better than optics. No question about it. Because David Miller, for example, in 2010, published a paper in Nature Photonics showing that the optical transistor cannot be at the best efficiency as a regular electronic transistor. And that's just based on the fundamental aspect of optics. So if we want to do digital system, we better stick with the electronics. So what optics can do much better is analog system. That's what we're doing over here, is analog. And also special purpose computing. In other words, for what application you would like to do it. Application like imaging, application like sensing, applications such as equation solving, vector matrix multiplication. Optics are fantastic. We do that. Yes, you can make that reconfigurable. You can make it programmable. But I don't want to throw away electronics. Electronics do a lot of great things that we would do there. Another point, by the way, is the noise in the system. So application that the noise is less sensitive. By the way, look at our eyes. Our eyes are analog system. There's a lot of noise, but it still works very nicely.
I have a couple of questions.
Sure.
First of all, I wonder whether you could do this work with a beam of massless neutrinos instead of optics. And secondly, I wonder if you had the solution to some integral equation or matrix eigenvalue problem. Is there a unique nanostructure which corresponds to that solution?
Thank you so much for your question. The first one with respect to the neutrino, I don't know. But in general, I would say any wave system. This can be applied to acoustic, for example. You can do it. Neutrino, I don't know, but I guess if it can be written in terms of a wave, that would be the case. But second part of the question, if I understand your question, let me repeat that. You're saying this system that we designed, let's say this Swiss cheese that we have there, is the shape unique for that particular kernel that we have? No. That's actually the beauty of it. In other words, when we do the inverse design optimization and you get this distribution over here, this will do that kernel. But that doesn't mean that's the only shape that would do the kernel. Other shape can do that too. And that brings us an interesting advantage. Because then there would be other parameters that you can actually specify. For example, one of them may have a better bandwidth than the other one. One of them may have a different Q than the other one. So if you like to actually add additional constraint, then the number of possibility of this shape become less and less. And at some point, eventually become unique. But actually, you don't need to do that. because the important thing is that they give you a shape that would give you that kernel with the given bandwidth that you want. And I'd be happy to talk to you in more detail if you're interested.
Well,
So I wanted to ask you about topology.
Sure.
Maybe that's implicitly already a thread in your talk that you haven't explicitly talked about. But so these metastructures are very efficient platforms also to engineer topology, essentially.
Sure.
Can you comment on that, how that could tie into these computing scenarios?
Yeah, thank you for the question. We did not consider topology in the sense of mathematics of the topology there. We used the optimization, inverse design to get to this point. It looks actually quite, kind of like topological, if you will, but it doesn't have that aspect. If you're referring to topology from the point of view of topological insulator and so on, no, this does not have that. But one can consider, by the way, that possibility, particularly because if you want to cascade this. Now, right now we have this one system, but the output of this could be the input to the other one. So some of the visions that we have is imagine in the near future, you have this micron size, switches, and you put several of them next to each other, and there would be a coupled equations. So you would be able to solve, a coupled integral equations that you would have there. There, topology may become interesting because you would like to make sure the output would be one way rather than the light coming back. But for now, we don't need that.
Thanks.
one question from
Thank you. You mentioned
I'm sorry.
here on
that
your
one, on the right.
your left.
Oh, I'm sorry, I didn't see.
Thank you. So you mentioned that the metamaterials, the structures are not unique to a particular operator.
Sure.
Is it possible to maybe generalize it to perform composite operations by tuning the metastructures, for example?
Thank you for the question. When you say composite, are you referring to the fact that because this is not unique, you can do more than one operation at the same time?
Yeah.
We did it. That's exactly the reason we did it.
But with the
Yeah.
same structure, by tuning
structure.
it differently.
No, that's what we said. We build one single structure that can solve two different integral equations at the same time.
But okay, but can it derive the answer from the previous operations to do further operations?
So you're saying that let's say you have one operation,
Yeah.
you find the answer,
Yeah.
and then what?
And then you use the same structure or maybe tune it in some way to perform another operation using that
I
result.
understand. That's what the reconfigurability come into play. That's our goal. Yes, that's our goal. In other words, we do this with one system, you find the answer, then you change it, use that answer in order to solve another problem, if I understand your point correctly.
But can you tune those structures?
That's what we're actually looking into phase change materials. Because phase change materials, you can actually change their index, their permittivities. That's the goal. Okay. That's what we also did the electronic version because we wanted to show that that would work as well. But I'd be happy to talk to you in more detail.
Yeah, we'll get one last question from Tamar, and then.
Yeah, thank you very much. That was a terrific talk. I was really impressed. So,
thank you.
My question is more about the properties of the incident light, and let me tell you why. Many years ago, we wrote a paper called Reconfigurable Ultra-Fast Nanoscale Logic Gates.
Mm-hmm.
And the way we do that, of course, this is just theory, I should say. And much more primitive than the beautiful things, the very complicated things that you do here. However, two aspects are perhaps relevant. First, the way we made it reconfigurable is by choice of the polarization and the phase of the incident light.
Sure.
And polarization was one of the key results that we could derive out of it in theoretical work. So the polarization of light allows you to break the symmetry of right versus left, up versus down. And it also allowed us at that time to make the same, to construct the same structure and change the function of the logic gate from one to another by choice of the polarization and the relative phase of two sources. So here is my question: how do you feel about the properties of the incident light, like its phase and its polarization? And second, what should I understand about your choice of working with metamaterials? What does the material do for you that plasmonics, which we just used at that time, didn't do for us?
Sure. Thank you. Thank you for the question. Great questions. So with regard to the polarization and phase, you have a very interesting point. Here, by the way, we actually kept the polarization the same in these structures, but we didn't have to. In other words, we could actually chosen the polarization conversion from one to the other. In fact, one interesting possibility, rather than using two different frequencies in order to do frequency multiplexing, we could do it polarization multiplexing with regard to that. In other words, for one polarization, it will show different kernel than for the other polarization with respect to that. By the way, just as a clarification, our system, by the way, is analog system, not a digital system. So we are not after the logic gate aspects of that, just from the beginning, because we wanted to keep it in analog system. Now, with regard to the choice of material, with regard to plasmonic, what's really actually crucial is the design itself. The choice of material, you can choose different material as long as those materials would be able to actually design it like this. So for example, in the case of silicon, we use silicon simply because foundries can do that, but then we chose it with a different height. But one could have chosen, for example, plasmonic material. The only problem, of course, plasmonic material, as you know very well, is lossy. So we didn't want to go there. We want to actually to keep it in the low loss system over here in order to do that. I have other comments. I'd be happy to talk to you more in detail.
Let's thank Nader again for his great talk.
Thank you. Thank you very much.
I see that there's a lot of interest, so Nader is going to be around for the rest of the day. So I encourage him to catch him during the coffee breaks and the reception. So I would like now to turn the podium to IIN Director of Global Initiatives, Abraham Harris, Professor of Material Science and Engineering, the founding director of the Northwestern University Atomic and Nanoscale Characterization Nuance, Professor
With that introduction, I should give a talk.
Yeah. Floor is yours.
Thank you, Koray. Good afternoon, everybody. It's a real delight and honor to introduce our next speaker, who's the final speaker for this event, Professor Hongkun Park. Professor Park it's a little long introduction, but I'll tell you it's worth it, and you stick around, and it'll be certainly worth it. Professor Park is the Mark Hyman Jr. Professor of Chemistry and Professor of Physics at Harvard University, which is sometimes affectionately known as the Northwestern of the East Coast. He's also a member of the Harvard Quantum Science and Engineering Graduates Program, the Broad Institute for Harvard and MIT, the Harvard Center for Brain Science, and the Harvard Stem Cell Institute. It's amazing. Yeah. Professor Park earned his bachelor's degree in chemistry from Seoul National University, graduating summa cum laude, but also as a valedictorian. And after a year of mandatory military service, as most of you know, with the Republic of Korea Army, he went to Stanford University to obtain PhD in chemistry under the mentoring of Richard Zare, focusing on the photoionization dynamics of nitric oxide through angle and energy resolved spectroscopy. For many of you know that relates to atmospheric chemistry, a very classic problem that he dealt with and made some very seminal contributions. So after that, he just crossed the bay on the other side to Berkeley, and he spent 3 years of postdoctoral fellowship with Paul Alivasados and Paul McEwen when he was there at Berkeley at the time, Lawrence Berkeley National Lab, where most of us came to know his work on electron transport through individual nanocrystals and nanocrystal arrays. And then Professor Chark joined the faculty of Harvard Department of Chemistry and Chemical Biology. He has very broad interests. As you can imagine, it focuses on fundamental studies of nanoscale electrical, optical, and plasmonic devices that operate based on quantum mechanical principles. Professor Park's work encompasses development of advanced nano and microelectronics tools designed to interface with a living cell, which has been a theme, as you notice today. Cell networks as well as organisms. His research in other side on the solid-state quantum optoelectronics seeks to create solid-state devices that operate at the single quantum level, truly paving the way for breakthrough in all optical computing and solid-state quantum information processing. Additionally, he focuses on tools, crafting nanoscale tools and probing the living cells in the network with a particular emphasis on understanding brain functions. His efforts also include development of ultra-sensitive magnetic, electrical, and temperature sensors using diamond color center, a very emerging problem, addressing complex challenges in condensed matter physics, molecular structural determination, and biological sensing. Now it is honors, if you can imagine, distinguished honors. Some of them include Ho-Am Foundation's Prize in Science, the US Department of Defense, famous Vannevar Bush Faculty Fellowship, the NIH Director's Pioneer Award, the David and Lucille Packard Foundation Fellowship, and Alfred P. Sloan Research Fellowship. He also received the Scientist of the Year Award by KSEA and Camille Dreyfus Teacher Scholar Award. In addition, he has several prestigious lectureships, including the Cowley Lectureship at the Delft University of Technology, the A.R. Gordon Distinguished Lectureship at the University of Toronto, and the William Draper Harkins Lectureship at the University of Chicago for the South. Before I ask him to join, I just want to mention that yesterday his flight was delayed by many hours, and he could have gone home and had a martini. Instead, he decided to come and join us today. And talking about martini, unlike James Bond, he can have his martini either shaken or stirred. So with that, let me go to Hongkun.
Thank you. Okay. Let's see whether this works or not. Hopefully it does not, so that I can escape from talking about this. Does it work? Oh, it works. Oh my God. Okay. First of all, I'd like to thank Chad and the organizers for giving me a chance to come here and give a talk here. It's such an honor and pleasure. And I would like to thank Vinayak about that wonderful and lengthy introduction. That was the longest introduction I've ever heard. So I'm not so sure whether I should thank you or not. But at least this is the last talk. So what can I say? I think that I have until the dinner time, right? So yeah. So today I will tell you about what my students are working on. As you can tell, my mom gave me a lot of things, but not a volume control. So I probably do not need a microphone, but we'll see how this goes. I will lower it as much as I can so that I do not wake you up during your sleep. Okay, so today I will tell you about our efforts on quantum information science, in particular on an atomically thin canvas. Before I start, indeed, my group works on a lot of different things. So I want to give you a brief introduction on what we are working on. We concentrate on nano and quantum science. We make small nanoscale materials and how to deal with them and understand their behaviors. Once we do that, then we apply them to a lot of different types of applications, including quantum and bio applications. So toward that goal, we are working on atomically thin quantum canvas, which will be the focus of today's talk. We will show you how we are using atomically thin materials to define lots of different kind of quantum simulators. In particular, today I will focus on one particular simulation, Wigner crystal quantum melting. We also work on defects in diamonds, say nitrogen vacancy centers in diamonds, silicon vacancy centers in diamonds, and use them for a variety of different applications. For example, together with Amazon Web Services, we are building quantum communication network throughout the Boston so that we can actually do eavesdrop-free quantum communications. We also use them for sensor so that we can actually build nanoscale NMR that goes toward single-cell NMR applications. And thirdly, This is slightly off topic, but the thing is that we also work on brain-machine interfaces. In fact, about 11 years ago, I was at in this same podium, and then gave a talk about our nano-structured interfaces with biology. And we made some progress after that. Of course, we never worked really hard, so it's a little progress toward that. I will show you 2-slide introduction about that. So in this particular effort, basically what we are trying to develop is a tool for brain sciences. We want to talk to neurons and learn what they're doing in the brain. So toward the end, we by now have dedicated CMOS chip that we designed together with our collaborators, Tony Hum, that can couple with the neurons, thousands of neurons at the same time. We can use this CMOS chip to image what neurons are doing, or we can actually use them to stimulate the neural activities. So you can consider this as a specialized camera chip that can talk to the neurons. This is a real-time movement of the brain tissues that we actually we took using this 4096 pixel camera chips. You can see that there are lots of different neural activities going on. By analyzing this, you can actually isolate each and every neurons in that network. There were about 15,000 of them that we were recording from, out of which we can actually build the connectivity diagrams of that. So using this, you can learn a great deal about what's going on inside that particular tissue. And then we are actually using that particular tool to do lots of different things. But that's that. We're not going to talk about that, right? So today, instead, we'll talk about atomically thin quantum canvas and how we are using it to realize interesting quantum circuits. So how do I start? Well, yesterday I've heard that this should be a very general talk. So I'm not so sure how general it'll be, but the thing is that at least I can try to make it general by talking about something like these crap. No, I didn't say that. Okay, so quantum actually is making a lot of noise nowadays. Some hyped, some true, but the thing is that certainly there are lots of people talking about quantum, and then there are lots of people claiming wonderful things out of quantum. And then many of them are true, and then we are indeed making lots of progress toward that. And people are building quantum computers out of that, quantum communication networks out of that, sensors out of that, and what have you. Now, some people call the current age as second quantum revolution. The first quantum revolution happened in 1920s. And at the time, people knew about the Schrödinger equation, Dirac equation, what have you. Now we call it second quantum revolution. Why? It turns out that we are not doing any new science per se, but we learned how to control the quantum system very, very accurately. So second quantum revolution, if anything, it's all about control. And here is an interesting parallel. So in 1999, when I first became a faculty member, I went around and met Chad, and I think that the first talk that I gave in one of those nano conferences was that nanoscience, and I said the same thing. It's all about control. We need to learn how to control the nanoscale systems. We need to control the surface chemistry. We need to learn how to do this, that. The same is true for quantum science. We need to control individual quantum systems to do useful things out of it. And people are learning a great deal about how to do it. Some examples. This. Some stupid bitmap movies, right? These are amazing things. Why? Because these bitmap movies were made of individual atoms emitting single photons. So all those dots are individual atoms that we are controlling that are emitting single photons, and we can make the movies out of them. Similar things can happen with solid systems as well. This one is a movie. As you can tell, somebody had more money, so this is made up by IBM. These are solid-state atom-like systems that can act just like an atom. And by controlling the electricity, you can control those atomic properties very, very accurately and use it to build a quantum computer. That's what IBM and Google are doing. So using these very well-controlled quantum systems, people can now start to do some primitive. Please do not say this to Michel Lukin, one of my great friends. Primitive is not what he says in his usual talk, but the thing is that some computing, for example, and then some very useful things. For example, when you actually have complete control over the individual quanta, then you can do real quantum computing. And people are making great strides toward that. Now, what we have in our system is not yet that level of control, but rather control over the density of the quanta and the interaction between the quanta and then other types of external parameters that we can control. Even using that, you can do useful things like quantum simulations. People actually have been using these quantum computers to do so-called quantum simulations so that they can learn a great deal about the material properties, Hubbard model systems, and what have you. What we are trying to do in my group is to do very similar things using electrons and excitons, electron-hole pairs within atomically thin materials. That's what we are trying to do. Okay? So, what are the materials that we are dealing with? These atomically thin semiconductors, known as transition metal dichalcogenide monolayers, or multilayers, or heterostructures, or what have you. So these are nothing more than essentially 3 angstrom thick semiconductors that are 2-dimensional. And then they can hold electrons, the holes, essentially absence of electrons, or electron hole pairs known as excitons. And they interact strongly with electric fields, light, magnetic fields, and what have you. We are using those knobs to control that system. Okay? And because these are naturally atomically thin, they are only 3 angstrom thick. Actually, this is a nanotechnology conference. They are 0.3 nanometer thick. Okay? So they are 0.3 nanometer thick, so the particles, electrons, and holes are interacting very, very strongly. And additional advantage is that they interact very strongly with light as well, because they hold so-called excitons, electron hole pairs. And those excitons interact strongly with charged particles like electrons and holes. So by simply looking at where those exciton resonances happen, essentially color of the light that comes out, you can learn a great deal about how the charges are moving inside that system. And we'll use that extensively from now on. Okay? So what we wanted to do was to use this as a canvas to draw lots of interesting things, lots of interesting quantum things. In order to do that, then we actually had to do lots of different things in order to control them and then learn how to work with them. For example, to start with, we actually had to learn how to make them very, very clean, and then how to add the textures to it, and then make devices out of it. And I will select one particular example of Wigner crystal today, and then tell you a little bit of a story using these 3 storylines. First, how to prepare a clean canvas, because if you want to draw a picture, then you need a canvas. Then I will tell you a little bit about lucky story about finding Wigner crystals in these materials. And then thirdly, the final story about how we actually used it as a simulator of quantum melting of electron Wigner crystals, which even with the supercomputers and then quantum Monte Carlo simulation, people still do not theoretically predict. So start with clean canvas. This is really a simple story that you guys all know about. If you want to draw a picture, the first thing that you need is a canvas, clean canvas. The same is true for electronic circuit. You all know that. We wonder about the complicated electronic circuits which has lots of nanoscale transistors. These are possible only because we have very, very clean crystals of silicon. This is probably the purest crystal that you can find in the world. And the reason why we can define all those complicated circuits is because we have these silicon ingots. The same is true if you actually want to build a quantum circuit on atomically thin materials. You need very, very clean atomically thin canvas. And so when we first started to work on this, the first thing that we had to do was how to achieve that. And then after lots of different kind of work, that finally we learned how to tame their properties, disorders in those systems, and then stuff like that by essentially passivating them using another 2-dimensional materials, hexagonal boron nitride, and suspending them. By doing so, we made them so clean that these materials exhibit excitonic properties, which is macroscopically homogeneous and spectrally homogeneous as well. How do you prove that? Well, by making a mirror. You probably have seen the mirror this morning, right? I usually don't because I know how ugly I am, but the thing is that you guys usually do. So when we think about a mirror, typically they have thickness. Well, typically is not the right word. They always have thickness because in order to reflect light, they actually have to have a thickness which is comparable to the wavelength of light. But in a particular situation of perfect atomically thin materials, it turns out that you can actually have you can make a monochromatic mirror. That happens like this. Let's say that you actually have atomically thin semiconductors which holds spectrally and spatially homogeneous excitons. And then you shine one particular wavelength of light which is resonant with that particular excitonic transitions. As it undergoes these excitonic transitions, the light acquires pi phase shift, destructively interfering with transmitted light and constructively interfering with reflected light. So even with atomically thin 3 angstrom thick materials, as long as they are truly clean, then you can actually reflect the light, which is resonant with that exciton with 100% of efficiency. Sounds like easy thing to do, but it turns out that even with the cleanest optical system that you can find, like gallium arsenide quantum wells, the maximum reflectivity people have gotten is something like 20%. It turns out that with our system, we can get 85% of reflectivity at cryogenic temperatures, as long as they are below, say, something like 150 Kelvin, which tells us that, indeed, we can actually deal with these systems and make them very, very clean, so that we can start to draw a picture. Of course, once you actually have that, then you can start to play with it. So this is what, say, one of my students did. For example, by selectively gating and stuff like that, he made a 3 angstrom thick, essentially, reflectors or projectors out of it. Useful? No, it's not useful, but it's funny. You can actually draw like physics and stuff like that. But the gist of it is that we now know how to make them clean enough so that we can start to draw a picture, quantum picture. Then we start to draw some kind of picture, quantum pictures like Wigner crystals. Now, here's the punchline. Okay, so the next 2 slides will be about Chad, so we'll see. Okay. I wanted to teach him some Schrödinger equation. How about that? Yeah, I don't think that will be possible, but we'll see how that goes. So electrons in 2 dimensions or 3 dimensions. Normally, we think of them as freely moving. That's what we usually see in a metal, right? But Eugene Wigner, almost 90 years ago, actually almost exactly 90 years ago, predicted that if you make the electron dilute enough, then they should form crystals, known as electron Wigner crystals. This is very counterintuitive. You make them very, very dilute, and they start to freeze in space. Why? Now here comes the Schrödinger equation. This is the only slide with an equation, so follow me. So this is nothing more than a Schrödinger equation, which has kinetic energy part and Coulomb interaction part. Even you understand that, right? Yeah. OK, now to a simple change of variables using average distance between electrons, Rs, which is inversely proportional to density, square root of density. Then you note that this kinetic energy part scales with 1 over Rs squared, while potential energy part scales with 1 over Rs, which means that if Rs is really, really small, then this part should dominate, becoming a gas. Nothing more than a kinetic energy. Potential energy you can ignore. But if Rs becomes really large, then you actually have to consider potential energy, and you can ignore kinetic energy. It becomes solid lattice. So that's what happens. When electron gets really, really dilute, they freeze in space and form a crystal. That's known as Wigner crystal. The trouble was that these were very, very hard to realize, especially in the quantum mechanical version. People, after that prediction, had tried to make these things quite hard. Actually, some people claim that, for example, so-called fractional quantum effect was discovered while they are searching for Wigner crystals in quantum mechanical version of it. Whether that is true or not, I'm not so sure. I think that is true. But the thing is that at least people actually made a classical versions of it by spraying electrons on the liquid helium surfaces. These are individual electrons on liquid helium surfaces, or trapped ions in gas phase. But these were all classical in a following sense. The energy of the electrons, kinetic energy of the electrons, was determined by the thermal energy. If you want to do it in a quantum mechanical version, and the kinetic energy is dominated by the quantum kinetic energy, you actually have to go to a solid state version. But the thing is that in order to get there, you actually have to essentially you have to get to the ultra low electron density, by which time essentially almost every crystal, including gallium arsenide 2-DEX, actually disorder dominates, and then you never get to the Wigner crystal. Can we get there using our atomically thin materials? It turns out that we can. One of the reasons is because we had luck. In these systems, it turns out that the electron mass is such that the kinetic energy is much lower than in the gallium arsenide. And we actually have optical probe which can sense how the electrons are moving around the excitons quite sensitively. Using these two facts, we could actually make Wigner crystals and then study them. So this is a device that we first discovered Wigner crystals, electron Wigner crystals. And it turns out that it was in the bilayer format for a reason that is obvious. We didn't actually search for Wigner crystals at first. We were making these devices for other reasons, and then we found something weird, and then banged our head for about 6 months, and then figured out that it was the electron Wigner crystal. So what we made was the structure that looks like this. There is 2 layers of atomically thin semiconductors, molybdenum diselenide monolayer, separated by insulator, hexagonal mononitride. And then we actually have a bunch of different electrodes so that we can control the electron density and hole density in each layer separately. And then what we do is to shine the laser light here and then see what happens to exciton spectroscopy. And then essentially, while changing the electron density in each layer, measure the essential intensity of those things, and then plot it. And when you plot it, you get something like this, so-called charge density diagram. As a person who started the career, independent career by doing electron transport studies, this is quite satisfying. Basically, you can see how the electrons behave in those materials by just looking at the light intensity. One funny thing happens, though, when we actually look at that NN region, where both layers have electrons at different densities. There, it should be dark because there are electrons around. And then I do not want to get into the details, but when electrons are around, freely moving electrons around, then the exciton intensity should go down. But along certain directions like this, then suddenly it does not go dark. What it means is the following. When the electron density in top and bottom layers make certain integer ratios, 1, 1, 4, 1, 7, 1, 3, 1, then suddenly those free electrons do not act like free electrons. Now, I'm stupid, but when you see from experiment out of blue 1 to 1, 4 to 1, 7 to 1, something like that, there must be something significant about it, right? And then it turns out that those are indeed integer ratios that demonstrate that there is a Wigner crystals. In a single layer, Wigner crystals should be triangular lattice. When you actually want to form bilayer Wigner crystals in a commensurate way, there is only certain integer ratios that are possible. That happens to be 1 to 1, 3 to 1, 4 to 1, and 7 to 1. Exactly what we found. So this is an evidence of electron Wigner crystal in a bilayer form. And by studying them, we can actually learn a great deal about them. For example, we can learn how they melt as you add thermal energy, thermal melting. But we can also learn how they melt as we increase the density, so-called quantum melting, or example of quantum phase transition. So the last part will be about that, because a lot of people are interested in how that happens. Okay? But before then, I need water. Okay, let's talk about quantum melting, or some bullshit like that. I'm quite liberally using language, so what can I say? Okay. At least, I'm making fun of myself, So the basic scientific question, and this one was a real question, and until this day, there are some debates about exactly what's happening. How does the quantum melting happens? So basically, as we increase the electron density, Wigner crystals should become gas or fermi-liquid, more known form of electrons. But exactly how that happens was a question. People actually have been studying this theoretically for a long while using a variety of different methods. And then using the most advanced quantum Monte Carlo simulations using supercomputers, people showed that that should happen when the average distance, which is essentially normalized by the Bohr radius, is around 737. But exactly how that happens is still unknown. Well, we think that we know, but the thing is that at least some people were debating. Why were they debating? So think about it. Let's say that you start with low-density Wigner crystal. And then as you increase density, it becomes fermi-liquid. And then if it were going through the first-order phase transition, and then there is a mixture of phases, then that's usually how that happens, right? Ice melts with water, right? Coexistence phase. The only problem is the following. This is a no-no. Why no-no? Because this is a low electron density, this is high electron density, which means that there is electric dipole moment. If you have a bulk electric dipole moment, you know what happens? Bad things happen. When you have bulk electric, charge separation, bad things happen. So it is energetically unfavorable to form those macroscopic phase separation. So what happens? Well, people believe that it goes through so-called microemergent phases. There are nanoscale puddles of different phases that actually coexist. But these are not just a coexistence in the following sense. It's a distinct thermodynamic phase. Exactly what that means, I don't know. But theorists say that. So what we decided to do was to study that, because we can now make electron Wigner crystal as Wigner originally envisioned. In this particular case, since we now know that there is a Wigner crystal, we started with monolayers, and then studied the Wigner crystals using so-called Umklapp resonance. What is that? Well, usually, when you think about the electrons in a crystal lattice, because atoms are arranged in a periodic fashion, electrons spill them and then make a band. In this particular case, we actually have electron crystals and excitons spill them. So exciton dispersion relations form so-called Umklapp resonances, which shows up as an additional peak. And by studying them in detail, you can learn a great deal about how the electrons are arranging themselves. And also, by essentially adding polarization, as Tamar stated, in this particular case, circular polarization, you can learn a great deal about the magnetic order as well. Now, I do not want to prolong this particular discussion, so without getting into any details, by doing all that, and it took for us to do all those analyses about 1 year and counting, we can now determine phase diagrams during the quantum melting. This is temperature, this direction. This is density of electrons. And then we now know how the Wigner crystal melts and what kind of phases that they undergo as it goes through this quantum melting of Wigner crystals. It turns out that it does not go directly from Wigner crystal to fermi-liquid. It goes through those coexistence phase. We do not call them microemergent phase because we do not know exact structure of it yet, and we are trying to study that. And there is also additional interesting phase that nobody has seen. It turns out that there are fermi-liquid-like behaviors with enhanced magnetic properties. Exactly what they are, we do not know. But at least we can now get there by making Wigner crystals on our atomically thin canvas and study them in detail. So that was fun. Now, so this is one example of the quantum simulations that we actually have been trying to do using our materials and then our knobs that we actually have. For example, other things that we actually have done was this pentalayer graphene studies that we did together with Longju at MIT. And then in this particular case, we studied, quarter metal, half metal, multi-ferroelectricity and what have you. But this is a story that even I do not understand, so I do not talk about this. And we also study other types of things as well. But at least, hopefully, I have given you a flavor of the things that we actually have been trying to do. We wanted to realize solid-state quantum systems where we can realize lots of interesting functionalities. So in order to get there, what we started to do was to learn how to deal with materials and make them very, very clean. And then we learned what kind of basic properties that they exhibit, and then use them in order to realize electron Wigner crystals. And then once we learned how to make them, then we started to use them in order to learn what's happening in between. So all these studies would not have been possible without all these wonderful students. Actually, as you can tell, what I do is just go around and give a lousy, lousy talk. These are the people who deserve all the credit. So Wigner crystal quantum melting studies were pioneered by these two guys, Jiho Sung and Jue Wang. And Ilya Astolis, who is now a professor at Wisconsin, actually did all those theoretical studies. And then other people here actually have done lots of the other studies as well. Yu Zhou, who is now a professor at University of Maryland, actually started the Wigner crystal studies. Giovanni Scuri, who is now looking for a job, as he's currently postdoc at Stanford, actually studied that mirror, atomically thin mirrors and stuff like that. And I have wonderful collaborators. That was not my intention. Wonderful collaborators in Mikhail Lukin, my friend for the past 20 years. We have been collaborating for the past 20 years without fighting. That's an achievement in itself. And Philip Kim, graphene experts who actually, in my opinion, should have won the Nobel Prize together with the other people, but he didn't. So, but the thing is that he's a wonderful expert who actually is really amazing scientist. And Eugene Demner did all those theoretical studies and then all those funding. And thank you very much.
It's a tour de force. Thank you. So we have time for a few questions. Look for people with the mic around. George first.
So your phases are really fascinating. Is there a critical point associated with these phases? I mean,
yeah, that's another question that we are actually arguing together with flat iron theorists. Andy Millis and other people are actually doing the quantum Monte Carlo simulations for that and stuff like that.
Okay,
and then this one, yeah, because it go through those microemergent phases, it's
Right.
probably not just going to be a second order phase transition with quantum criticalities and stuff.
Yeah, good, thanks.
Yeah.
Oh, I have a couple of questions.
Yes, sir.
First of all, since you mentioned we're in the second quantum revolution, shouldn't second quantization be a powerful tool to describe these interactions in the system? And the other thing I was wondering about is whether you could study an elementary chemical process in the crystal and the liquid phase to see how the dynamics might change in going from the solid to the liquid phase.
Yeah. So the first one, it's an interesting question. Second quantization, at least the current versions of, say, second quantum revolution does not necessarily involve, for example, more advanced forms. It's more or less about, Schrödinger's equation and stuff like that. So it's not yet there, but the thing is, it eventually will get there. In fact, actually, some people are using these quantum simulators in order to study the string theories and stuff like that. So some aspect of it is there, but the thing is, it's not explicitly there. Secondly, about your questions about chemical systems and phase transitions, yes, indeed, that is main goal of these quantum simulator people. Making a general purpose quantum computer is, at least as of yet, although Misha and then IBM and Google are making great strides, are not that easy to achieve yet. We are making great strides, but we are not there. But the thing is, in terms of analog quantum simulations of material properties and chemical properties, it might be easier to get to. And that's where a lot of people are trying to put their efforts toward. Yeah. But still, there is a long way to go. We are just starting to learn how to play. And then hopefully it'll someday not be just a plane, but rather something important.
Did you make any speculation now as to how a dynamic process might change going from the liquid crystal to the Fermi liquid?
No, that's exactly the type of question that now we are studying, together with those theorists. Essentially, how to study them, what kind of question is the most relevant one that we should probe, and then how to probe them. And then we are actually actively working toward that. If we can actually study quantum dynamics of these quantum melting, that'll be really, really wonderful. I'd love to do that. Hopefully next time, when I come back in 10 years, then I might be able to tell you about that.
Any other questions? Maybe if I could ask you one. So given that the single layer are so potentially sensitive to defects and strain, do you see the role of substrate to be an important one?
Yeah,
or,
absolutely. And that's one of the reasons why our devices are suspended, so that they do not see
any surfaces.
Yeah.
Okay. Over there. Oh, okay, sorry. Go ahead.
Great talk. Can you explain your material choices? So are there other parameters beyond effective mass of electrons? Because other systems like basque phosphorus can provide lower effective mass compared to MOS2.
Interesting, yeah. There are lots of different considerations that you go into. For example, why did we concentrate on molybdenum diselenide instead of tungsten diselenide? It turns out that, as we have shown in 2017 paper, there is so-called dark exciton, which is optically inactive lower energy state, which complicates the studies and stuff like that. The same is true for black phosphorus. They are wonderful systems, but we do not know how to tame their disorders as well as we do in this particular system. So there are lots of different considerations that go into, but those are certainly interesting systems to think about.
And my second question would be, in terms of probing them, how much defects play a structure, and how do you know where to probe for crystals?
So when we make them really well suspended and then stuff, then they are really spectrally and spatially homogeneous. So we do not have to worry too much about where to probe. But in typical devices, there are still some disorders. So my students sometimes go through and then find the best spot. So what I actually tell my students is that, first of all, you should make multiple devices and see the same thing. Second of all, you should actually go to multiple spots in these devices and see the same thing. Until then, don't come back to me and tell me about stories.
Don't go home, right? Yeah. Okay.
I do not say that. I'm not that bad. I'm bad, but not that bad.
Okay, going once.
Okay.
Going
thank you.
Twice. So thank you again, Professor Howard. So we have a short break, and we'll reconvene here in the same room in about 20 minutes at 3:10 sharp. See you back. Thank you.
Thank you.
this thing on? All right, great to see everybody. Welcome back. My name is Ted Sargent. I'm a faculty member in chemistry and in electrical and computer engineering at Northwestern University, and I'm a very proud member of the IIN and of the community. And it's really great to get to chair this panel session. You already know all of these panel members because they've given really exciting talks today, and so I'm not even going to introduce them because there they are, and they're well known to you. And I wanted to dive right into a first question. I'm going to ask the same first question to each of the panel members, and I'm going to go in this sequence starting with Jinwoo. But before I do that, I wanted to mention to the audience that after we hear from this first round from our panelists, I'm going to open it up to you for your questions. You could pick it up. You could pick up on my theme from the first question if you like, or you could take us in another direction. I have a second question that I'll get to about partway through the panel today. And so I'll sort of interrupt the audience interaction for halfway through, go through my second question, and then we'll turn it back to you. So do please start to think of your questions. So panelists, the first question. Looking into the future, what big, pressing scientific questions can nanoscience and nanotechnology uniquely answer? And what highly constraining technological roadblocks is nanoscience and nanotechnology poised to overcome? So, to summarize, both scientifically and technologically, what are the key things that nano can enable? And then what are the key challenges that we should deploy it to tackle? And I'm going to start with Professor Jinwoo Cheon.
All right, so thanks, Ted. And I think one of the challenge that that we have is in terms of the nanomedicine as a delivery of nanomaterials in terms of cargo, any specific position and specific application for example disease treatment. So people have envisioned that nano will be very good for delivering cargo into anywhere that you intend to deliver. But the fact is that according to many studies, that's a bit too exaggerated. So it's very difficult to have a targeted delivery into any disease site. So in terms of nanoparticles, people found that the delivery rate success is very low. Even sometimes nanoparticle even less than 1%. So what should we do? And we kind of promise that we could deliver the challenge without any means. In terms of the nanoscience was believed to answer that question. But I think that's what we are challenging. Is how we have so nice molecules and biochemicals and synthetic molecules that will cure the disease. But how are we going to deliver majority of them into the targeted area? I think that's the big question. And then to do that, I think the 5 months visionary statement saying that what if we have some nanorobotics, nano machines that can propel by themselves, go around and find their target and then specifically deliver cargo and cure any problems associated with that area. So I think that's a good question. And not, in terms of the scientific, how are you going to build up that kind of robotics? Probably the bottom approach. That's nature's evolutionary results. But can we synthetically or biologically assist the process to build up those things? Hopefully. 50 nanometer, or 100 nanometer in that size range, like a virus, right? Then do we have that capability? And if so, I think that would be the answer of some of the the promises that we have made. I think 60 years ago, 70 years ago.
Great, thank you, Jinwoo. Well, I said I was going to go around the panelists, but I have a follow-up question for Jinwoo first, and then I'm going to go around the questions. But before I ask my follow-up question, I have to tell my Jinwoo Cheon story. So I think Jinwoo and I first met roughly 2001, 2002, something like that, in a place called Ottawa. which is notable for being very small and very cold. You see, he remembers. That's how notable it is. And the thing I remember most about meeting Jinwoo, I don't know, I was maybe 17, 18 years old. I was an assistant professor. Jinwoo was 12 or 13 years old. He was probably already had tenure. And Jinwoo presented the most beautiful tetrapods I've ever seen in my life. And then I reminded myself today that those were in a 2001 JAX paper, which is kind of how I remember the date specifically. And there was this like beautiful tetrapod, but there was like atomically resolved images of the interfaces between the different planes that caused it to be a tetrapod shape. It was gorgeous. So the question for you, Jinwoo, is you talked about delivering cargo, but what is the role of shape and size and perhaps surface functionalization? Like, what are the critical issues that remain unanswered in nano as they relate to cargo delivery specific to shape, size, and functionalization?
All right. I think it all matters, right? Probably the surface functionality is probably the most important, and also the size. You don't want to have micron size. You may want to have few nanometers up to 100 nanometers. I think that's probably the size regime. But the problem is that it's all diffusion limited, and we don't have, once you inject the particles, we don't have much control over those nanoparticles or delivery vehicles. So I think that if you could see where those are located and where they are, and then once you have them to capability of self-promotion, proportion, meaning that somehow it maybe it's better to have them to navigate by themselves, like the automotive cars, and maybe you want to have deliver a nano vehicle, but we don't know where the targeted area is. We don't know. So it's like you are just deploy some nano machines, but it'll find their way, because once we know where the disease are already located, maybe sometimes it's too late. So somehow let them just do automotively to find their way. So I think the biology and life science, we only debate. That's a Texas issue, right? How can we have the nano vehicle about 50 nanometer, and then it comes with maybe artificial components. Somehow they navigate by themselves and find the target. And then biology already gave us some knowledge associated, because the biology, the function itself is doing that. But once we could accomplish that, I think that would be very interesting.
Wonderful. Thanks so much, Jinwoo. All right, I am going to move along to Professor Nader Engheta.
Very good. Thank you. Thank you, Ted. I think what you mentioned, is very, very important, life sciences and the role of nanotechnology there. But in my opinion, another important aspect that nanotechnology can address and also solve the problem, but also face the challenge, is the issue of energy. I mean, we know all the AI development that we heard. In fact, as I mentioned in my talk in the past 2 days, Nobel Prize in Physics and Chemistry both have AI aspect. But the AI, particularly the way the tremendous amount of computation that goes there requires energy. And in a few years, we come to a point that we need another way of thinking about energy. And I believe nanotechnology is the vehicle towards addressing that issue. So how to actually do this type of computation with as low energy as possible. So clearly nanotechnology is a platform that can find and can explore the solution. But I would like to add a more general aspect to this. Obviously, we all love nanoscience and nanotechnology, and that works, on the nanoscale in space. But there are other extreme scenarios that also it would be nice to take into account. And that is, in time, attoseconds. That's another interesting direction of extreme aspects, which, if you recall, last year, Nobel Prize in Physics was given to the attosecond aspect. So it would be interesting to actually think about that and connection of that with the nanotechnology. And finally, also energy at the extreme, and that is attojoules. So eventually we're going to get towards those limits that we have there. And again, the physics and chemistry and the various aspects of nanotechnology can help us do that.
Great, thank you, Nader. I'll take a follow-up with you as well because there's so much in what you said, which is you gave a very specific example of how nanotechnology can play a role in what I would call energy conservation, or the world of data centers exploding. It's kind of diminishing the rate at which the energy consumption is exploding with them. But what about in energy production? I think there's many answers, but do you have a favorite area related to energy capture, energy conversion, where you also see a really significant role for nano?
Solar energy, obviously. I mean, that goes without saying. That's the thing that we have, in nature. And it's already, by the way, is a lot of activities going on all over the world, including the center, as to how, you actually use the nanotechnology in order to capture and harness the energy there. So clearly, that's something that, of course, is also sustainability aspects of that, and green energy would be very important. Clearly.
Great. Thank you so much. Professor Cato Laurencin.
Great. Well, thanks, and thanks for having me today. It's been a great meeting. Well, first of all, I want to preface my remarks that I don't believe that nanotechnology alone will solve most things. I think that nanotechnology is a great area of science, great tools that accomplish tasks in concert with other technologies. In the case of regenerative engineering, we have it as an important part of the toolkit or the toolbox that we use for regeneration. But alone, it's not the be-all, end-all alone. I'd say that last month I was at IFATS, which is the International Fat Society. There's actually a group, the International Fat Society, that gets together in a big room, and. And I said that to them, that, they were like anathema. I was like, as it turns out, fat is not going to solve everything. People were like, what did he say? So in terms of different societies I start by saying it's a tool, it's a part of the toolkit. So what are the things that are important? And I think that at our institute, we try to look at the end of the beginning. I tell my students, look at the end of the beginning. And if you look at the top 5 surgical procedures, I'm just saying off the top of my head, being done right now in the world, arthroplasty or hip and knee replacement would be in the top 5. And soft tissue procedures would be in the top 5 in the world. What if you could do something paradigm shifting in which those procedures are not done anymore? And how do you make that occur? So we think of the end at the beginning, and we think, sort of big picture, transformative types of science and transformative types of technologies that make that happen. So that's where I see in terms of, changing the landscape. 5 years later, we're not doing, 2 or 3 of the top 5 procedures that we're doing with, and we're doing them because we've got something better, not because we're just not doing them, but we're doing them because people are getting better, people are healing better with these areas. And so I think that's where we're looking. That's one of the goals that we look at. The other goal is, how do we harness the body's ability to heal itself? And so we do a lot of work thinking about self-healing and harnessing the body's ability to heal. And what we learn in the other areas, can be harnessed for the areas of nanotechnology to sort of address these areas. I'll give you one example. So as I talked about, earlier today, I work with salamanders, axolotls, and we chop off their arms. I don't want people to be squeamish, but they regenerate their arms. In fact, we've actually found a way that we can actually we can actually make a hole in their bone, and if we divert a nerve into that hole and take skin from a special place and put it over that area, it can regenerate a 3rd limb, which is pretty cool. Which is a great model because it allows us to see a more aggressive model for regeneration. Well, when we've done that, we've been able to find certain cells that start to appear during that regeneration. And these are, I was mentioning it yesterday night, these are groups of cells that are regenerative They're interspersed in the soft tissue, and they are dendritic. In other words, they have these processes that come out and they connect to each other. And so they're GRID, we call them grid cells. And we've been able to, we're working to isolate. I met someone last night who's going to help me isolate them. I'm not sure who it is, but someone in the room here. And we've also found them in mice, which means that there's hope that these grid-type cells that we know are key in terms of limb regeneration will be there. So one of the things that we propose to do, I hope no one's going to copy us, one of the things that we propose to do is to actually create an artificial grid matrix. We've got the cell type, and we've identified enough that we think we can recapitulate that. And then, but we think that nanofiber technology, we can mimic, with nanofiber technology, we can mimic the dendritic portions that connect these cells together. And so maybe we can't make grid cells or make the grid, but maybe we can make an engineered grid that we can use and insert during the limb regeneration process or amputation process, to create a limb regeneration process. And so that's a sort of a big picture where we bring technologies together and include nanotechnology with that. The other area that we're very interested in is how do we, with all the ways in which we're regenerating, how do we monitor the regeneration process and make changes in real time? And we think that nanosensors biological nanosensors will be important to be able to do that, especially in terms of joints, knees, shoulders, in terms of being able to insert them. We've worked with scientists at UConn on creating sort of nanosensors that actually sense and respond once they're injected into the knee. And I think it's going to be really important in the future for monitoring.
Wonderful, thank you. Well, before we move on to Hong Kong, I wanted to encourage all the panelists to start to think of a story or a visual image that is weirder than the salamanders growing back their third leg. I think we should make a little competition. I'm going to call it an arms race. Over to Professor Hong Kong Park.
But wait a minute, I just want to make it very clear that it may be an arms race, but I have a leg up on this.
All right. All right, with that, Professor Hong Kong Park.
Yes, this is first of all, normally when you go to these kind of panel discussions, then they usually give out the questions first, say a day before, and they say, why don't you actually think about it and look smart? Ted is actually nothing like that. He's tough, indeed. I've never heard about these questions before. But the thing is that it was a really tough question in the following sense. He actually added the word uniquely. And then that one threw me off. I can certainly tell you a lot of important scientific and engineering problems that nanoscience might be able to contribute. But the thing is that in terms of uniquely solving, that is where I was stuck. So nanoscience and engineering is one of those unique things that are, where the discipline is defined by the length scale, right? So I guess it's between 1 nanometer. I guess that 3 angstrom doesn't count, right? Yeah. Between 1 nanometer to 100 nanometers or something. If you define nanoscience and engineering that way, then what problem can we uniquely solve? So in order to think about that, I guess that we should think about what kind of natural processes and natural things that are uniquely, how can I say, matched in terms of length scales with those length scales. For example, take an example of, say, one of the favorite examples by Munji Bawendi, last year's Nobel Prize winner. Say, that's a quantum dot. And the reason why quantum dot actually is one good example of nanoscience is because in those materials, exciton radius is such that when you actually make the particles into nanoscale, you can actually exquisitely control their optical properties, which you can use in order to make high fidelity TVs, right? So that was one example where nanotechnology was important because the length scales that are defined by the material size was well matched with the material properties so that we could actually find a unique solution. So are there other examples like that? One thing that comes to my mind is obviously related to biology because so many of the machineries in biology are naturally nanoscale. Proteins, although they are very small size, small scale, but the thing is that they are nanoscale machines. Many of the organelles and stuff like that are nanoscale machines. So I think that if you could really engineer nanoscale materials in such a unique way, you might be able to interact with biological systems and then interact in such a unique way. So that might be one example of uniqueness. Another example of uniqueness is chemical catalysis and stuff like that, where heterogeneous catalysis and homogeneous catalysis. Nanoscale is that in between that is unique, that you might be able to take advantage of heterogeneous catalysis and homogeneous catalysis and combine them together in the nanoforms. So that's one area that came to my mind. Another example is energy. For example, typical charge separation in the materials and stuff like that. Ted's beautiful work and then stuff. You might be able to harness the nanoscale in order to make unique machines that can take advantage of those. Although there are quite a few examples of that, and Ted actually does beautiful work. But the thing is that whether we are truly uniquely solving particular problems using nanotechnology, I'm not yet fully sure. And for example, our host example of spherical nanoparticles. That's another example where nanoscale materials and their composition is uniquely used in order to interact with biological systems. So, but I don't think that these are exhaustive. But at the same time, when we talk about nanoscience, and I've been on this one for the past 25 years, I started my independent career in 1999, and then that's when I first met with Chad. Even then, I do not know that many examples where we can proudly claim that nanoscience uniquely solved this particular scientific and engineering problems. I think that that's a challenge that is still left for us. I don't know. I'm not so sure whether I'm answering your question or I'm asking you a question.
You are asking me a question, but I asked the questions today, and so it's out of order. And
please, see, you stop.
And so I'm going to swiftly move on as a result to Professor Ting Xu. Thank you, Hongkun. Ting.
I think I probably will follow up on that. And I can tell you my personal experience. I think for me, nanoscience has been the tool that allowed me to recognize the relationship with myself and as well as me with my surroundings. And you can probably see from the research I'm doing, it really took quite a bit of turn over the last 10, 15 years. I've been in Berkeley for 18 years. I always say I'm a super postdoc. Because for us, we see many things. And nanoscience, at least my knowledge in nanoscience, come to meetings like this, learn things that completely out of my topic area, get me to begin to think about things very simple happening in your daily. I was pregnant with my son. I have to say I never learned biology to that level. And as you read biological books, right, think about this stem cell in body start to grow into this something that you're going to hold in your hand. That 10 months pregnancy, I was reading it at the level, I was like a sponge. But as you read things from the molecular cell biology or other books, and you start to put in this physical knowledge you gained from a lot of model system. I do block polymer self-assembly, look at thin films, and I deal with nanoparticles, nanocomposite, etc. So I would say because of the knowledge I had, it professionally helped me to think about life in a very different way. And I think that's fundamentally changed the way how we do research. And I can also tell you that as I get to know more what nanoscience could potentially do, and I have to say that sometimes really keep me stay up in the night. We had a lot of discussion with my husband, that is with ethics. A lot of things that are not published. But we as a scientist, based on the knowledge, we know what can potentially happen. There's not like a scary story trying to keep everyone on the edge like this is the end of the world. So, and I think more and more I'm more interested in looking into the ethics in nanoscience. I think that's something that as a community we must bring in as we train more young generation, because we are at that stage. What we do will impact what's going to happen for the next decades or centuries to go. I do polymers, I do plastic waste. There's a reason why I consciously choose that. Polymer made a mistake over the last 100 years, right? And it's a mistake that not just us, it's our offspring is going to pay. And you don't want that to replay for nanoscience. And nanoscience can do many things if it managed well. But I feel like as a community, it's important to bring that into a very important arm of research.
Thank you, Ting. Sure. Yeah. All right, we're going to go to the first round of audience questions. I'll say that you're invited to direct your question towards one panelist, and if you don't, then I'll do it for you. Because we're not going to have every panelist answer every question. We're going to move around a little bit. But it's, I think we got some folks with mics, and we're ready for questions. And some gentlemen up front. Oh, no, actually, Chad.
Oh, thank you, Ted. Actually, yeah, I'd like to a stab at answering each of these questions for each of you, because I think you don't do it justice. Nader, all of your work is uniquely enabled by nanoscience. The tools that allow you to miniaturize, to build those structures, allow you to either prove or disprove your hypotheses. On the medical side of things, if you look at it, we're living it. You go back 20 years in drug development, and the top 10 drugs were all small molecules. So small, chemically precise structures. Chemists played a huge role in enabling that and drive much of the pharmaceutical industry. You look today, there are no small molecules in the top 10 drugs. And in fact, the top drug is a nanodrug. It's a really crude nanodrug. So we've moved from really chemically precise structures to larger, more complex structures, because we know we can engage new pathways and attack disease in different ways. The next wave is going to focus, I think, again on chemistry. How do you take and make large, complex structures very precise? Because if you can make them precise, then you can systematically address many of the issues that you're talking about. The problem is we've been stuck for a long time in using really crude materials to solve really complex problems. And I think the real work's just beginning, which is how do you begin to make these structures with the eye of a chemist and the precision of a chemist so that you can open up precision medicine, so you can build structures on the biological side. You take something like CRISPR, one of the greatest, I think, nanostructures ever discovered, and by the way, isolated and put together in a test tube. That's a type of nanotechnology, and it's a real nanotechnology in that case. But there's more you can do with that. If you can begin to modulate that machine, you can begin to control how you deliver it, where you deliver it, and how effective it is. So I'm very bullish on this, not just of it playing a role, but uniquely solving certain problems. And I don't think we should lose sight of that. It doesn't mean it's going to solve all problems. I think Cato made a lot of good points in that regard. But there are still enormous challenges, and I think it's really important for the community to identify them and try to drive it.
That's great. Thank you, Chad. Well, first, before I refer that to a single answerer, I'm going to mention that as moderator, I have the power to mute the microphones for the live television audience. Keep that in mind, that I could exercise that power. But I'm actually going to refer this one to Hongkun, because I think Hongkun was the strongest about asking the question about uniqueness and perhaps also necessity. So Hongkun, how do you respond?
Two, the up points. Chad, as you just said, what I said 25 years ago has some meaning, right? It's all about control. Yeah. So secondly, there's a reason why Chad Merkin is a spokesperson for the nanoscience. You can, his eloquent, rebuttal for my crude statement certainly proves that, right? So I completely agree with you that, but the thing is that when I said the uniqueness of nanoscience, I did not necessarily include all areas of bioscience, which includes, CRISPR machineries and other things. So, but the thing is that if we enlarge it that way, and I agree with you that there are so many unique things that you might be able to do going forward. But the thing is that we actually have not been, how can I say, vocal about advocating that as a part of the nanoscience, or actually convincing the others that that's a part of the nanoscience and stuff like that. But I think that we should certainly.
Do you think there's some drivers in terms of how you fabricate some of the things?
Yeah, absolutely. Yes.
Those tools, which are going to be unique nano tools, are going to either enable it or not?
No, I think that they are unique nano tools that are enabled or not. But the one reason why I didn't think of it that way was because many of the tools that we are using now, for example, lithography and stuff like that, we can call it nanoscience tools, or we could call it existed before I came to the nanoscience, or nanoscience was a word. So, but the thing is, of course, all those are just the semantics. But the thing is, I completely agree with you now that I've heard that. For example, defining it that way and broadening it that way, there are so many unique things that we might be able to do as a chemist and nanoscientist using these nanoscale structures to do unique things. And then on that front, for example, I will just, this is not answering your question, but I was just curious about what you guys think. For example, one of the reasons why I got into this bio thing that I never, as an undergraduate student, I never took biology course ever, period. I did not even take general biology, but I became interested in biology partly, and actually mostly, when I realized that living cells is the most amazing thing. It's essentially, it's a mother of all the emergent properties out of nanoscale machineries, right? We actually assemble a bunch of nanoscale somethings, like DNAs, proteins, and stuff, assemble them together and then compartmentalize them together, compartmentalize them into a particular region, and then they suddenly become alive. Exactly what that means, I don't know. But the thing is that we might be able to do similar things using nanoscale materials. If we actually enlarge the portfolio of nanoscale materials, and then if we actually have control over them, and then if we learn how to control them to such an extent that we can assemble them in a unique way, or in a self-organized way, we might be able to make something truly unique that might actually, make Ting not sleep, because exactly what they will do, we do not know. But the thing is that that's another thing that is scary, but also exciting to me. So I don't know. This was just completely rambling. Sorry about that.
I think it's a management, right?
Yeah.
And I think we can manage. So that's, nothing really, even with CRISPR, right? There's a lot of ethics discussions.
Yeah.
If you look at those, there are experiments done on human that was not supposed to. So that's where, biomedical area does really well. Students come in, their ethics class, they have to go. And it's not like we have to invent things new. We just have to really take things and mix in the uniqueness of nanoscience and then go from there.
Thank you, Ting, and thank you, Hongkun. I'm going to take the next question. Any other questions?
Hello. So I have a question about talking about nanoscience to the general public. So I teach a seminar on nanotechnology to first-year students, and one of the things we spend a lot of time thinking about is how we've heard about nanotechnology in the news or in sci-fi and all of those things. So in terms of getting people to understand the power of the future of nanotechnology, there's an aspect of making sure it's not fearful for people who are not involved in technical science. So how do you view your role in communicating your work to the general population? And what tools can we provide young scientists with to be able to do this very successfully in their careers?
Thank you for your question, which I'm going to refer to Professor Ting Shu.
Thank you. I appreciate that. I do polymers, and it doesn't really take a lot. So I'm, on one end, I'm a contributor to the plastic waste. On the other end, I do quite a bit of outreach with our podcast when talk about plastic waste. And the key question people ask me, do you see a viable future? And I do. And I think I did this thing with PBS. And I think it ends with, what do you think is a viable path? And I have to say, nanoscience is your solution to solve the plastic waste. Polymer by birth is a nanomaterial because the single chain dimension happened to land in that particular dimension. So that's why there's a lot of emerging phenomena associated with it. And people talk about microplastic, et cetera. But the cure in the end, whether you wanted to do degradation, modification, upcycling, or any chemical transformation, it has to happen at the nanoscale. And that was determined by the nature of the material, happened to be a nanoscience. Yeah. And I think for others, for organic nanoparticles, I think there has been quite a bit of biocompatibility, et cetera. That's where part of it. I think if we as a community were being proactive, to channel the information to the community that we thought about it. It's one of the arm of design principle to look at the long-term impact, to look at both health as well as ecological, sustainability, environmental, you can even get into supply chains, earth abundance, et cetera. I think if we proactively address that, and I think we are doing not only ourselves something good, but also really serve the general public. Because by the end of the day, the whole reason we're here is really trying to make people live better, not because we need a job or we can do many other things. But I'm sure when you're going to fix people's knee or legs or arms, whatever, you want that patient to be happy.
Thank you, Ting. I like the question so much. I'm going to see if there's another panelist that wants to tackle it as well. We'll do it as an arms race. Just lift your hand if you. Any takers?
A leg race.
Well, I'll just say in the general gist of things, I think it's very important that we as scientists do much more in terms of educating the public. And we have to be a part, especially in terms of teachers. So we have an RET program. We have a research experience for teachers program at my institute. And we bring 2 teachers a year to our institute where they spend mainly the summer, but also during year time, and they work as scientists. Now, in a lot of communities, the average high school science teacher has an English bachelor's degree, and they coach the track team. And by the way, they do, biology and chemistry as their teacher. In fact, in some school districts, 50–60% of the science teachers actually don't have a science degree. And so it's really important to embrace, especially in terms of new technologies, to embrace teachers to do that. So these teachers come in, they learn the science, they conduct experiments, and our goal for them is for them to publish a paper or be a co-author in a paper by the time they finish. And we've been pretty lucky. Every teacher that's come in the door, obviously they're highly motivated. They've come in and they've actually published a paper afterwards that they can then bring back to their students, show the experiments, and use that in their classroom. And I think it makes a difference in demystifying, nanotechnology. It also provides tools, and we've actually now have this next generation of young people who are now coming to our laboratory because they've been taught by the teachers in the classroom and have been turned on by the work. So I think that as scientists, we need to do more. Now, this is just another plug for the Regenerative Engineering Society. And it's the first society that is for everyone, as I said, democratization. We want lay people to be members, and we actually have a lay person section of our society encouraging lay people to be involved, especially teachers. The journal itself, if you go to the website, I think this is where the first people do this, maybe not. The first person to start this way. Every journal has an abstract that's written at the 8th grade level for everyone. We have obviously a regular science abstract, but we have a lay abstract. And then we have our NSF REM research experience and mentoring students who are 8th grade to, they're K to 12, 8th grade to 12, and also in college students. They become our mini editorial board, and they review our abstracts to make sure that someone at their 8th grade level can read it. They're like, well, what do you mean by that? And so that's how we doubly reinforce. Someone says, why do you know it's at the 8th grade level? We have 8th graders reading our abstracts and editing our abstracts for us. And so I think it's really important that we embrace and bring people in science in general, nanotechnology being one part of it, but bringing young people in science and teachers in science.
Thank you so much, Cato. That's a wonderful initiative that you described. It's wonderful to hear about it. Thank you. It's inspiring. Next question. Can we go? Well, you decide. All right.
Hello.
Can we, maybe we'll go here and then we'll go to you after. So we've got a question in front of you at the front.
Yeah, what revolutionized the topic on computing after Dr. Engheta, right? Photonic computing. So what is the fundamental difference between photonic computing and quantum computing?
This is Professor Nader Engheta.
Yeah. Here, by the way, what we use as a optical computing over here is basically, classical optics goes there, and we use it as a quantity that will actually encode the information that we have there. So when we actually send the wave, the magnitude and phase of it, that's the information that we have and in the mathematics of it. And this wave goes and interacts with the objects that I showed you. And then the result is also based on magnitude and phase that we have there. So here everything basically is deterministic in the sense of that not being quantum. Although I have to say that the structure that we built could possibly also lend itself to being in the quantum level, although we haven't done that, but it could be possible to go through that. So this way of using optics, we are using it in a sense as an information carrier that goes through this, that we would be able to find that. Of course, it has its own, constraint. I didn't get a chance to talk about the noise that we have in the system, but this is, of course, analog system. An analog system is capable of actually providing application for some specific domains, very different than the digital electronics that we have there. It would be interesting to see how this approach that we have been working on could be actually relates to the system that when you bring the energy of the optics so low that then you deal with a few photons. That's actually one of the things that we are interested to pursue later on. We haven't done that, but to see what would happen if instead of just a simple wave that you're sending through this, you would have basically few photons go through that. So that's the one that we are doing over here. And of course, as I mentioned, there are certain, specific tasks that optics would do better than electronics, but there are tasks that electronics would do better than optics. For example, storage. I mean, electronics are very good from the storage point of view as compared, to the photonics one.
Wonderful. Thanks, Nader. All right, we did have a question at the back. Go for it, please.
Yes, hello. My name is Tom Wong. I'm with Illinois Institute of Technology. I'm an engineer by background. I've been a professor of electrical engineering. I work on microwave, and in recent years, I've been working on semiconductor nanoparticle in the plasmonics in the terahertz. But I wish to follow up on Professor Laurencin's comment about the work he's doing with the high school teachers, coming to do projects, research. Here in Illinois, we have a IMSA, Illinois Science and Math Academy, founded by the Nobel laureate Leon Lederman. And I myself served on the school district of Skokie for several years when my children were in school. And there I learned that the way we teach science in high school is quite different from where I was from. I grew up in Hong Kong, which had the education system at that time following the British system. We actually spread out the teaching of physics, chemistry, and biology over 7th grade until 11th grade. So all students interested in science, actually, they have to have physics, chemistry, and biology all through. But in the US, it's not the same. Usually students start taking biology, and then after a year of quite packed from what my perspective would be, and that person will grow into doing chemistry and then eventually physics, which was seen to be more challenging, maybe using math a little bit more. Then I had a discussion with Leon Lederman. He said that there are pros and cons of doing various things, but foremost, as what the Professor Laurencin said, that we don't have enough science teachers. And that creates a situation that if we want to use the resource of teachers effectively, the way what we are doing in the United States is a better way of doing it. But in the British public school system, they plan things differently. So all the children interested in science have the luxury, perhaps for lack of better terms, of doing 4 full years of all these 3 subjects. So I wish to hear what the expert would say from this point of view.
Thank you so much. So I'm going to refer this question to Professor Cato Laurencin, and then after, we're going to go back into the round of questions that I'm asking up here. Over to you, Cato.
Well, I think what we're seeing across schools and across science in general is a move toward what we call problem-based learning, or PBL, where a problem is provided and one needs to bring chemistry, biology, physics to be able to solve the problem. Same thing in medicine. In the old days, it was 2 years where you were just sitting in a seat and you just had to soak it all in. And of course, at the third year, you'd see patients, and then the fourth year, you actually sort of master it to a certain extent, and you could go out. But now, all these curricula are now doing problem-based learning where you're integrating over a continuum of time these different areas. And I think it's great. I think it's also great as someone who works in convergence and who works in the convergence of technologies, because I think it makes a stronger scientist where they have to actually find the information from a number of different sources to be able to bring things together. When we think about the work that we're doing, none of us are doing the same thing that we did 10 years before, which means that we had to soak up new information, like from this meeting today, in terms of all I've learned from my colleagues today, in order to be able to formulate new pathways to move forward. And that's actually the real learning and growing process that takes place. And so this problem-based education and problem-based learning is going to be, I think, for high schools and even for grade schools will be a part of it. It is an issue if someone leaves one school and goes to another school, because suddenly the problem-based learning system may be very, very different. But I think it's really going to be very, very key. And I think it's a key for America. And it says much about America in terms of the problem-based learning system. I was asked to come to China. This is pre-COVID, to talk about problem-based learning in engineering and problem-based learning in medicine, because I wore both hats. And their curricula was still very, very much based on the old school British and medical system, where on the medical side and also on the engineering side, where you take this course in a silo and this course in a silo, and then get a grade and then move on. And I think that that's a big advantage that we have, is this ability to integrate technology and science across different areas to be able to create new science.
Wonderful. Thank you so much, and thanks for your question. All right, we're going to go back to questions from here, and I'm going to switch up the order of answers as we go past the panel this time. So this time, the order of responses will be based on reverse alphabetical order, based on the second last letter of your last name, which obviously is Ting. Is going to go first, so get ready, Ting. So the question in this round is the following. It's a bit more along a policy line, a bit more perhaps advocacy. There is a lot of genuine and well-justified excitement about quantum, about AI, about synthetic biology. In fact, many of us benefit from that and participate in those fields as well. But it does present the risk that we could get missed. We could get kind of crowded out. So what strategies should we adopt as a community to make sure that the kind of the work that we do, which we believe to be so important, is funded, supported, believed in, that it attracts students, and that it attracts the minds of all the stakeholders who should be interested in what we do? Ting.
I've been very lucky. I have a friend, she is in AI, and basically they do algorithm to predict the weather as well as stock market. And I get a chance to work with her. She actually applied the expertise into my system. Actually, some of the work I talk about, the sequence translation, essentially based on that. We probably started a conversation maybe like 10 years ago, just because we're a personal friend. What I see is that, at least in my discipline, for soft materials, we are first of all, there's not enough data. The second is that for soft material, there's a very unique that we are not oftentimes going with the thermodynamic equilibrium. The energy, especially when you talk about the biology, is very much rugged. So that the system, there's a reason it's soft, because it's moving. When you start to get into that without much data, I would say the human intelligence is far superior. So there is that level of expertise that you gain. So I'm pretty happy. I don't think I'm going to be out of the job for the next 50 years. I may be over-predicted. The reason is that if you want to get into the computing side, even in the theoretical part, we are doing each skills. Atomic, there's ab initio, there's DFT, there's atomistic, there's coarse grain, there's Monte Carlo. If you ask someone saying, I work with each of them with a group of theoreticians separately. And occasionally people say we can really increase the size of the box to be able to give you some structure, from the atomic to a long chain. Sounds really good, but when you really dig through in there, you're basically saying that the field is not mature for AI. So AI for science, in order to make sure that you are not getting misleading, you need to have enough data, which we don't. And second is that I think AI scientists need to learn physical science. And I'm really proud. I basically co-advise a student from this mathematician group, and the graduate student, even though she's doing the algorithm data development, she can really interpret the physical meaning of the data. And I think that's where we need. I think we need to really educate the next generation so that those who are able, or the mathematicians can look at things from our lens instead of just simply treat them as a cold, hard data. And that's not the case. My sister also worked for Microsoft, and you will never believe she will call me. She said, can you deal with the thermal management in the chip? And that's like, here's my sister. She's well past 40 years old. She's been in Microsoft for ages. I never ever imagined she will ask a material science problem, because all she does data science for her master degrees, then she worked for Microsoft. I would say she's well ahead of game in terms of data science, artificial intelligence. But for her to ask me that question, the second thing is, can you extend the battery lifetime with non-lithium battery? And I'm like, sorry, I don't do batteries. And I don't do thermal transport. But actually, I began to look into the thermal transport and soft matter later a little bit. So I think the field are converging, and it's going to be up to us to really educate the next generation so that we can shape our discipline's future.
Wonderful. Thanks so much, Ting. Next on the rotation is the letter T, Professor Nader Engheta.
Okay. So I think that just to follow up with what Ting mentioned, I think the fields are dynamics. I mean, obviously, the fields don't have boundaries. These issues that we call, something, nanoscale, something we call it physics, AI, and biology, the boundaries are merging together, and that's a good thing. And I mean, collaboration, as Ting mentioned, is quite important because we can learn from a colleague expert in the other field. But that actually brings the students into play, and those becomes also expert of the future with the knowledge that you were mentioning over here. And I believe that actually is a great thing, part of science, because we always like to expand our knowledge and learn about other topics, and that will help us to come out with discoveries at the boundaries among the fields. I mean, you mentioned about AI and the connection, for example, AI with quantum optics. That's something that is quite could be fascinating, in the future. And then also the issue that I mentioned in the answer to the first question is that we are in the length scale that Hongkun mentioned. That some of the things work in that level, but also from the point of view of scale in time. I mean, that's something that less we talk about. But that's actually quite important from the point of view, and also energy as well. Ted, your question with regard to these are hot topics these days and so on, but these hot topics can actually merge together. So the interesting point is that what should be the connection among these hot topics, and those are the areas that would be quite fascinating for scientists to look into that, and that actually creates next frontier to that. So I really believe that these interest in this area is a good thing to have, but then we should look into beyond that, not just these in silos, as Cato mentioned, but also connection among all of them.
Wonderful. Thank you so much, Nader. Next up is Hongkun Park.
So, my apologies, but the thing is that, are we answering your question?
Well, the first two speakers did a great job. Now it's on you.
So if that's the case, then I will continue that line then. Because I thought that when you originally asked the question, you were talking about all those different disciplines actually emerging and then being hyped and then actually, essentially, how can I say, garnering oversized resources, and how we're going to maintain our, for example, nanoscience discipline or chemistry discipline, more traditional disciplines, and how we're going to educate the students.
That's exactly the question. But the first two answers are very diplomatic people, and we're waiting for your answer now.
Now that I clarified it, I think I did my role. I'm looking forward to Jinwoo's answer.
No, come on.
So I think that it is definitely true, and then I think that that was one thing that we realized over at least in my independent career, that happened a lot. Nanoscience was first wave, and then after that there was a brain science, synthetic biology, what have you, and then certainly, the popular subject actually comes and goes, and then along with it, the funds, right? So I think that was part of the questions that Ted was asking. But the thing is that that one is certainly true, but the thing is, the one thing that I also observed is nothing lasts forever, meaning everything goes through a hype cycle. They get overhyped first, and then they get depressed and then they become normal science again. And then I think that being flexible and being nimble in those areas, and then also having a core is important. Meaning, if you know what you do very well, and if you do it very well, I think that there are lots of opportunities that arises from it. And then if we actually, educate our students or work with our students, learn from them, and then make them really good at certain things, and then make them be open-minded, I think that they can also survive through these difficult times. And that's one of the things that I try to make sure that I do, although I do not do a very good job of. And then I think that the fact that, for example, this IIN generated such a wonderful student body who are going out there and then actually becoming a leader actually is a testament of that. That's not just because say, for example, Northwestern Nanoscience just said nanoscience the thing and then nothing else. That's not because of that. Although they did a beautiful nanoscience, the reason why they are so successful is because they are flexible and they can apply their knowledge base and then their expertise into a variety of different areas that are emerging. And I think that making the students flexible like that is an important part.
Thank you, Hongkun. We're going to go next to Professor Jinwoo Cheon.
Oh, yeah. All right. So I think the buzzwords, AI in quantum computing and synthetic biology and so on, I think the public understanding of this very low, and so per se the education, and we are talking about the educating younger people, but that are problematic because of climate change, and then some people don't really understand what it is about. And even though we had a highest summer in Korea for the past 100 years, it's very, very hot. I mean, it's just growing. People are always, having difficulties, and it's getting worse and worse. And then we are talking about climate change, but we have so many different ways of promises. Like, okay, so solar cell, we have renewable energies, we have all sorts of different wind and so on. But as scientists and engineers, I don't think we clearly deliver the message from our side to the public, and that's I think there was one question from the audience. I think that's very important. And how are we going to effectively and then accurately deliver the messages to the public, and especially the people who are leading the country or society, and the politicians and so on. So I think there is a big gap between us and then those people. And then probably Chad had a good experience with PCAST and so on. And then I think in Korea, for example, we had a huge budget cut last year because of our the top level policymaker found that first of all they think that AI, quantum computing, were you talking with those people, by the way? So they are investing so much at once, but they cut drastically in other funding, So that has been big trouble. And that, we are now negotiating a little bit, talking. But it happened, and I think it's for sure that the policymakers want to have a advancement of knowledge to make the society better, and so on. But I think the understanding of science in general, not the top level and then the intermediate level, and those people, somehow there is a big gap between us. Very little conversation, discussion, and so on. So it ended up with going kind of, not wanted, way, meaning that there's a lot of confusion now. Should we go for AI? Should we go to computer? Or should I just stick with organic chemistry? Should I go for, other, physics and so on? So it's a bit, problematic, and I think it's clear in U.S. and so on, other countries. So I think that it might be. I think the IIN has done great job for public, outreach, and at the same time, educating younger people, next generation scientists and engineers, so on. So I think that has been great, but still, I don't know how we are going to deal with, already grown-ups, those, policymakers, and then, the leaders of the society. I don't think that their understanding of science is very low at this moment, unfortunately. So what should we do?
I have a story for you about that. I have a Korean policymaker science knowledge story for you, Jinwoo. I was in a car with a bunch of friends driving on the bridge, coming back from Korea University and KIST, back over to SNU. And I asked him, how's research, how's his funding? And he said, oh, our prime minister doesn't like perovskite solar cells. So there's no funding. There's no funding for us as a result, yeah. So they must be very knowledgeable, because I don't think people here would know what a perovskite solar cell is. So, yeah. Right. All right, so we're going to go to Cato, and in fact, this is going to be our last panelist, and it's actually going to be our last intervention because we're getting close to time. And so I'll invite Professor Cato Laurencin to give us the last word.
Wow, okay. Well, so AI and how I feel about AI. So I'm going to give you a little story. And so in 2015, actually 2014, I was elected to the Chinese Academy of Engineering, became an academician. And as a part of that, you actually have to give a talk. I was one of we have 4 foreign members that were elected. So I went to Beijing and gave my talk. And actually afterwards, like that next day, the same day, there was a magazine that came out, and they handed me a magazine. The China News Daily did a story on it, and I'm like, oh my gosh, first of all, it's all in Chinese, so I can't read it. And I'm like, what do they say? Did they say something bad? Like, this is, and it said, well, the person translated, no, it's good. Was it good, or you're just saying that? No, it's good. What does it say? Well, it says, Laurencin's moonshot. Oh, okay. All right, sounds good. And so it talked about our work that we're planning to do and what we're thinking about and how it's a moonshot that's there. And when I think about moonshots, I think about President Kennedy, who in the early 60s, like maybe 62, said, we're going to the moon. We're going to go to the moon by the end of this decade. And everyone was like clapping and things like that. But in 1962, the only thing that the astronauts had in 1962 was what? Tang. That was it. Tang. You're before your time. But the point is that the only thing that we knew about astronauts is that they drink Tang. That was their major technology that they had. And actually, they had no idea how to get to the moon. I mean, I'm sure when they said, oh my gosh, but they had no idea how to get to the moon. But by 69, that's the reason why we did it in 69. We had to because the president said, we'll do it in this decade. And that's the reason why we're able to do that. And so the things that we do in regenerative engineering are often called moonshots. At least there are in China. And so because of that, we need every tool, and we need to be early embracers of any tool that comes in terms of being able to move things forward. And I think that AI is a very, very important tool for us to be able to move into. The reason I like AI is the fact that everybody can be an expert in AI. You know, I was on an AI panel, which of course there are a lot of AI panels, and the person that was next to me was like, I have a PhD in AI. I've been doing AI for the last 30 years. Well, I said to him, if you've been doing AI for the last 30 years, you haven't been doing AI, right? Because this isn't your father's Oldsmobile, right? It's another phrase. But anyway, the point is that the AI that people are talking about now has nothing to do with whatever you studied 10 to 15 years ago. And every person that's now working in the field now, it's a new field. It's a brand new field. And so we are early embracers of AI. So, just as you talked about, we are now working with computer science department, with the math department, in terms of having grad students that are working and interacting with us, trying to co-advising students that work in AI to work with us in our area. I'd have a prediction. I predict that in terms of regeneration research, if a component of your research is not involving AI, you probably won't get funded. Probably won't get funded for a lot of practical reasons. Number one is the fact that we use a huge number of animals. I just hope that, as I've always said before, I hope that heaven is not a rat heaven, because I've probably operated on a number of rats, and you go to heaven and you find out, my God, the pearly gates at St. Michael is a rat. Yes, we've been waiting for you. So the whole point is that efforts to minimize the number of animals being used is a huge area, and it's going to be growing and growing. And so your ability to be able to use predictive AI in terms of the work that you're doing, to use a minimum number of animals to be able to get to your outcome, is going to be so important. And those that have mastered that and know how to use that effectively, will be able to show that they've used that effectively, will be able to not only be able to use fewer animals, which I think is going to be needed, but also be able to move the area forward. If you think about the things that we've done with nanotechnology and nanomaterials to predict, and what we've learned over the years in predicting, what if we had AI algorithms that we could have used earlier? I think we would have gotten where we are much faster in terms of the work that we're doing. So we have AI as a part of, part of the pillars of what we do, and we embrace it there, and we bring people in, and in this world of convergence, we want people to be transdisciplinary, meaning, collaborative means like you've got something, I don't have something, so we work together. Multidisciplinary is that I've got a little bit of you, you've got a little bit of me, and we work together. But transdisciplinary means that you've got that we all have absolute mastery of these different areas to some level and extent. And in a transdisciplinary way, we work together with our various levels of mastery, but mastery is there. And so I think that mastery in terms of AI is going to be very, very important in terms of regenerative engineering. But I think in all areas of science, because I think it's going to be a component. It's not good. It may have peaks and valleys, like nanotechnology did, but I think that it's going to be there, and I think it's going to be an essential tool in the toolbox for regeneration.
Fantastic. Thank you, Cato. Chad.
I think on that note, we will close things out. Let's thank Ted and the speakers for a great discussion. I also want to thank this year's sponsors one last time, Abbott, American Elements, Emitech, Boston Microfabrication, Dachi, Joel, and JLL. Again, wouldn't be possible without their generous support, so let's give them a hand. I also really want to thank the IIN staff again for their brilliant management skills in putting this whole event on. It's not an easy thing to do, but they seem to do it flawlessly, so let's thank them as well. And then finally, up the stairs, we've got a reception, and we invite you all to go up there and have a drink and have some food and enjoy the rest of the day. But this is really a lot of fun. Thanks for coming, and we hope to see you next year.